Hello. Multi-electron system. Ohm's rule. The electrons enter in a set of degenerate orbitals. First singly, then pairing of electrons takes place after the orbital become half-filled. For example, nitrogen 1s, 2s, 2p, 3 electrons, single electrons. Pauli's exclusion principle states that no two electrons in an atom exist in the same quantum number, that is, four quantum numbers. Same. For example, helium, that is the spin quantum number difference. This is also wrong. This is also wrong. This is correct. According to the Pauli's exclusion principle, two electrons within an atom cannot possess identical sets of four electronic quantum numbers. 1s, 2s, 1s, 2s. This is the correct. Electron first and second, principal quantum number 0. Magnetic quantum number 0. Spin quantum number plus half and minus half. Okay. For helium, this is the 1s2. So principal quantum number 1. Azimuthal quantum number L equal to 0 to n minus 1. So 1 minus 1. So 0 to 0, 0. Magnetic quantum number also minus L to plus L. So 0. Spin quantum number plus half and minus half. Application of Pauli's exclusion principle. Pauli's exclusion principle is used to determine or verify the maximum number of electrons that can be accommodated in a cell or subcell or orbit. Example, K cell n equal to 1, L equal to 0, M equal to 0 cannot exist. Cannot exist 3 electrons. Principal quantum number 1, 1. Azimuthal quantum number 0. Magnetic quantum 0. And spin quantum number plus half and minus half. Third electrons minus half or plus half. So this quantum number similar. So quantum number of third electron is identical with the first or second electron, which is against the principle that is not valid. For LCL, 2s and 2p, n equal to 2, L equal to 0, 2n minus 1, 0 to 1, 0, 1, L equal to 0, m equal to minus L to plus L, 0 to 0, 0, so L equal to 1, m equal to minus 1, to plus 1, minus 1, 0, plus 1. First, second, third, fourth, fifth, sixth, seventh, and ninth electrons. See, this may plus or minus half, so it is not exist, cannot exist. If we attempt to assign the quantum numbers of 9 electrons in this level, its quantum numbers becomes identical to one of the remaining 8 electrons, which is against the Pauli's exclusion principle, so that L cell can accommodate the maximum 8 electrons. Justification of Hund's rule: the orbital electronic configuration having the high spin multiplicity state are more stable. In the early days of quantum mechanics, it was proposed that on-pair electrons in different orbitals are apart, so electron repulsion energy is reduced and attain the maximum stability. However, this explanation is now obsolete. Accurate quantum mechanical calculations 1970s have shown that the true reason is that the electrons is singly occupied orbitals are less effectively screened or shielded from the nucleus, so that such orbitals contract and electron nuclear attraction become greater in magnitude. Total spin multiplicity 2s plus 1. S is spin quantum number for D5, that is the 5. So now one queries arise after the subshell become half fill. Why electron pair up in the orbitals rather than entering the higher energy levels? The answer is that it would require higher energy and will be less stable. When all orbitals fill singly, the incoming electron has two choices, either to pair up with other electrons or to go the higher energy level. However, energetically, it is more favorable for the electrons to pair off in the same subshells rather than going in the next higher subshells. Importance of Ohm's rules: it plays an important role in interpreting paramagnetic and diamagnetic behavior of substance, transition in rare earth metals, lanthanides. Above principles, the electrons first occupy the subshells having the lower energy, then it occupies the subshells having the next higher energy, n plus 1 Madelung rule. It is said that the subshells having the lower n plus 1 values is filled, then the electrons occupy the subshells with the next higher n plus 1 values, n principal quantum number, L azimuthal quantum number. Subshells n plus 1 for is n plus, no, sorry, n plus L. So 1, 2s, 2, 3p, 4, 3d, 3 plus 2, 5, and so on. Hence, energy of these subshells are in the order 1s, 2s, 2p, 3s, 3p, 4s, 3d. Limitation of above principle is not able to predict the electronic configuration. Example, electronic configuration of Zn plus 2 should be argon 4s to 3d8, but spectral study shows that electronic configuration of Zn plus 2 should be argon 3d10. Above principle does not agree with some of the transition metals. Chromium 24 of configuration 3d4 4s2, but actual configuration argon 3d5 4s1. Similarly, copper, argon, aurum, platinum have also of configuration and the actual configuration as shown in this table. Actual configuration of above elements due to the special stability associated with the half fill and full fill d orbitals. Electronic configuration of lanthanum 57 and 89 according to ordered lanthanum 57 5f1 5d0 6s2 89 radon 51 6d0 7s2. The electrons should enter in the n-2 f orbitals, but In fact, the last electrons enter in the n-1d orbitals, and actual electronic configuration is lanthanum, xenon 5, 0, 51, 6s2, 59, radon, 0, 51, 7s2. Energy level diagram across the D block elements, energy nucleus of blank energy level diagram, 5p, and list one is. According to n plus 1 rule, energy of 4s orbital is lower than 3d, hence up to the atomic orbital 20, 1s, 2s, 3p, 3s, 3p, 4s, 3d. However, with increasing atomic number, the relative position of the stabilities of the orbitals tend to change gradually. Hence, for d block elements, the energy of the 4s orbitals becomes greater than 3d. Similarly, energy of 5s orbitals become greater than 4d and energy of the 6s orbitals greater than 5d. So order of energy levels tends to become 1s least and the last, the highest is 60. Reasons for stability of half-fill and completely filled orbitals. Symmetrical distribution of electrons. Symmetry leads to stability due to lower energy, so that orbitals either half-fill or full-fill have the most symmetrical and reduces the energy and then increases the stability. In case of chromium, see argon 4s1 3d5, 4s 3d. So similarly, the copper expected configuration 3d4 4s2, but observed configuration 3d5 4s1. Similarly, in case of copper, expected configuration 3d9 4s2, but actual configuration 3d10 4s1. Exchange of energy the 4 plus 2 and equal 10. In the case of chromium, in the electronic configuration of 3d4, the electronic configuration exchange in the 6 ways. So hence the exchange maximized nicotine in the half-filled piece of cell. The electrons with the parallel spins have the freedom to create themselves exchange between their orbitals. This reduces the energy and called exchange energy. So in case of 3d4 and 3d5, we compare the exchange energy is higher in the 3d5. So this is stable, reduces the energy. Okay, it's all about the multi-electron systems. Thanks for watching and request you all like, comment, share, and subscribe. Thank you for patience. That's now. Bye bye. See you again.